Prologue, Bangkok, 1989. The afternoon rains have ended, leaving the early evening air briefly free of smog and allowing that distinctive Thai perfume, frangipani with a faint note of sewage, to waft over the shiny streets. I hail a tuk-tuk, a three-wheel motorcycle taxi, and hop aboard. My young driver has an entrepreneurial smile as he turns around and begins the usual interrogation of male travelers. So ... you want girl? No, I see. Long pause, eyebrows slowly raised. You want boy? No. Longer pause, sound of engine sputtering at idle. You want ladyboy? No, I answer, a bit more emphatically, nonplussed at the idea that I give the impression of desiring this particular commodity. I got cheap cigarettes. Johnny Walker. No thanks. Undaunted, he moves on to the next category of his wares. Now with lowered voice. You want Ganya? No. Coke? No. Iba? Nope. A whisper now. Heroin? No. Voice raised back to normal. I can take you to cockfight. You can gamble. I'll pass. Just a little bit irritated now. So, faring, what you want? Prick key new, I respond. Those little mouse shit peppers. I want some good, spicy dinner. My driver, not surprisingly, is disappointed. As we tear through the streets to a restaurant, blasting through puddles. I'm left wondering, aside from various shades of illegality, what do all his offers have in common? What is it exactly that makes a vice? We humans have a complicated and ambivalent relationship to pleasure, which we spend an enormous amount of time and resources pursuing. The key motivator of our lives, pleasure is central to learning, for we must find things like food, water, and sex rewarding in order to survive and pass our genetic material to the next generation. Certain forms of pleasure are accorded special status. Many of our most important rituals involving prayer, music, dance, and meditation produce a kind of transcendent pleasure that has become deeply ingrained in human cultural practice. As we do with most powerful forces, however, we also want to regulate pleasure. In cultures around the world we find well-defined ideas and rules about pleasure that have persisted throughout history in any number of forms and variations. Pleasure should be sought in moderation. Pleasure must be earned. Pleasure must be achieved naturally. Pleasure is transitory. A denial of pleasure can yield spiritual growth. Our legal systems, our religions, our educational systems are all deeply concerned with controlling pleasure. We have created detailed rules and customs surrounding sex, drugs, food, alcohol, and even gambling. Jails are bursting with people who have violated laws that prescribe certain forms of pleasure or who profit by encouraging others to do so. One can fashion reasonable theories of human pleasure and its regulation using the methods of cultural anthropology or social history. These are valid and useful endeavors, for ideas and practices involving human pleasure are certainly deeply influenced by culture. However, what I'm seeking here in the compass of pleasure is a different type of understanding, one less nuanced, perhaps, but more fundamental. A cross-cultural biological explanation. In this book I will argue that most experiences in our lives that we find transcendent, whether illicit vices or socially sanctioned ritual and social practices as diverse as exercise, meditative prayer, or even charitable giving, activate an anatomically and biochemically defined pleasure circuit in the brain. Shopping, orgasm, learning, highly caloric foods, gambling, prayer, dancing till you drop, and playing on the internet. They all evoke neural signals that converge on a small group of interconnected brain areas called the medial forebrain pleasure circuit. It is in these tiny clumps of neurons that human pleasure is felt. This intrinsic pleasure circuitry can also be co-opted by artificial activators like cocaine or nicotine or heroin or alcohol. Evolution has, in effect, hardwired us to catch a pleasure buzz from a wide variety of experiences, from crack to cannabis, from meditation to masturbation, from Bordeaux to beef. This theory of pleasure reframes our understanding of the part of the human body that societies are most intent upon regulating. While we might assume that the anatomical region most closely governed by laws, religious prohibitions, and social mores is the genitalia, or the mouth, or the vocal cords, it is actually the medial forebrain pleasure circuit. As societies and as individuals, we are hell-bent on achieving and controlling pleasure. And it is those neurons, deep in our brains, that are the nexus of that struggle. These particular neurons also comprise another battleground. The dark side of pleasure is, of course, addiction. It is now becoming clear that addiction is associated with long-lasting changes in the electrical, morphological, and biochemical functions of neurons and synaptic connections within the medial forebrain pleasure circuit. There are strong suggestions that these changes underlie many of the terrifying aspects of addiction, including tolerance, craving, withdrawal, and relapse. Provocatively, such persistent changes appear to be nearly identical to experience and learning-driven changes in neural circuitry that are used to store memories in other brain regions. In this way, memory, pleasure, and addiction are closely intertwined. However, addiction is not the only force responsible for experience-driven changes within the brain's pleasure circuits. The combination of associative learning and pleasure has created nothing less than a cognitive miracle. We can be motivated by pleasure to achieve goals that are entirely arbitrary. Goals that may or may not have an evolutionary adaptive value. These can be as wide-ranging as reality-based television and curling. For us humans, even mere ideas can activate the pleasure circuit. Our eclecticism where pleasure is concerned serves to make our human existence wonderfully rich and complex. I like to tell the students in my lab that the golden age of brain research is right now. So it's time to get down to business. This sounds like a cheap motivational gimmick, but it's true. Our accumulating understanding of neural function, coupled with enabling technologies that allow us to measure and manipulate the brain with unprecedented precision, has given us new and often counterintuitive insights into behavioral and cognitive phenomena at the levels of biological processes. Nowhere is this more evident than in the neurobiology of pleasure. One example: do you, like many, think that drug addicts become drug addicts because they derive greater reward from getting high than others? The biology says no. They actually seem to want it more but like it less. This level of analysis is not only of academic interest. Understanding the biological basis of pleasure leads us to fundamentally rethink the moral and legal aspects of addiction to drugs, food, sex, and gambling, and the industries that manipulate these pleasures in the marketplace. It also calls for a reformation in our concepts of such virtuous and prosocial behaviors as sharing resources, self-deprivation, and the drive for knowledge. Crucially, brain imaging studies show that giving to charity, paying taxes, and receiving information about future events all activate the same neural pleasure circuit that's engaged by heroin or orgasm or fatty foods. Perhaps, most important, analysis of the molecular basis of enduring changes in the brain's pleasure circuitry holds great promise for developing drugs and other therapies to help people break free of addictions of many sorts, to both substances and experiences. When I was a postdoctoral fellow at the Roche Institute of Molecular Biology in the early 1990s, I was fortunate to work with Sid Udenfriend, a pioneer in the biochemistry of the brain and a real mensch. Sid's favorite pedagogical phrase, usually intoned at the bar, was "It's always good to know a little chemistry." I couldn't agree more. It would be possible to write a book exploring the brain's pleasure circuits that was free of not only molecules but also basic anatomy. But that sort of spoon-feeding would require ignoring some of the most interesting and important issues, and so that's not what you'll find here. If you come along for the ride and work with me just a bit to learn some basic neuroscience, I'll do my best to make it lively and fun as we explore the cellular and molecular basis of human pleasure, transcendent experience, and addiction. Chapter 1: Mashing the Pleasure Button. Montreal, 1953. Fortunately, Peter Milner and James Olds didn't have perfect aim. While postdoctoral fellows at McGill University, under the direction of the renowned psychologist Donald Hebb, Olds and Milner were conducting experiments that involved implanting electrodes deep in the brains of rats. The implanting surgery, conducted while the animals were anesthetized, involved cementing a pair of electrodes 0.5 millimeter apart to their skulls. After a few days of recovery from the surgery, the rats were fine. Long, flexible wires were then attached to the electrodes at one end and to an electrical stimulator at the other, to allow for activation of the specific brain region where the tips of the electrodes had come to rest. One fall day, Olds and Milner were testing a rat in which they had attempted to target a structure called the midbrain reticular system, located at the midline of the brain, at the point where its base tapers to form the brain stem. This region had previously been shown by another lab to control sleeping and waking cycles. In this particular surgery, however, the electrodes had gone astray and come to rest still at the midline, but at a somewhat more forward position in the brain, in a region called the septum. The rat in question was placed in a large rectangular box with corners labeled A, B, C, and D and was allowed to explore freely. Whenever the rat went to corner A, Olds pressed a button that delivered a brief, mild electrical shock through the implanted electrodes. After a few jolts, the rat kept returning to corner and finally fell asleep in a different location. The next day, however, the rat seemed even more interested in corner than the others. Olds and Milner were excited. They believed that they had found a brain region that, when stimulated, provoked general curiosity. However, further experiments on this same rat soon proved that not to be the case. By this time, the rat had acquired a habit of returning often to corner to be stimulated. The researchers then tried to coax the rat away from corner by administering a shock every time the rat made a step in the direction of corner B. This worked all too well. Within 5 minutes, the rat relocated to corner B. Further investigation revealed that this rat could be directed to any location within the box with well-timed brain shocks. Brief ones to guide the rat to the target location and then more sustained ones once it arrived there. Many years earlier, the psychologist B.F. Skinner had devised the operant conditioning chamber, or Skinner box, in which a lever pressed by an animal triggered either a reinforcing stimulus, such as delivery of food or water, or a punishing stimulus, such as a painful foot shock. Rats placed in a Skinner box will rapidly learn to press a lever for a food reward and to avoid pressing a lever that delivers the shock. Olds and Milner now modified the chamber so that a lever press would deliver direct brain stimulation through the implanted electrodes. What resulted was perhaps the most dramatic experiment in the history of behavioral neuroscience. Rats would press the lever as many as 7,000 times per hour to stimulate their brains. They weren't stimulating a curiosity center at all. This was a pleasure center, a reward circuit, the activation of which was much more powerful than any natural stimulus. A series of subsequent experiments revealed that rats preferred pleasure circuit stimulation to food and water. Self-stimulating male rats would ignore a female in heat and would repeatedly cross foot shock, delivering floor grids to reach the lever. Female rats would abandon their newborn nursing pups to continually press the lever. Some rats would self-stimulate as often as 2,000 times per hour for 24 hours. To the exclusion of all other activities. They had to be unhooked from the apparatus to prevent death by self-starvation. Pressing that lever became their entire world. Further work was done to systematically vary the placement of the electrode tips and thereby map the reward circuits of the brain. These experiments revealed that stimulation of the outer surface of the brain, the neocortex, where sensory and motor processing mostly reside, produced no reward. The rats continued to press the lever at chance levels. However, deep in the brain, there was not just a single discrete location underlying reward. Rather, a group of interconnected structures, all located near the base of the brain and distributed along the midline, constituted the reward circuit. These included the ventral tegmental area, the nucleus accumbens, the medial forebrain bundle, and the septum, as well as portions of the thalamus and hypothalamus. Not all these areas were equally rewarding. Stimulation in some parts of this medial forebrain pleasure circuit could support self-stimulation rates of 7,000 lever presses per hour, while others elicited only 200 per hour. In addition, a hollow needle can be implanted together with the stimulating electrodes to inject drugs directly into the pleasure circuit. Illustration by Joan M. K. Ticko. It's hard to imagine now, but in 1953 the notion that motivational or pleasure reward mechanisms could be localized to certain brain regions or circuits was highly controversial. The dominant theory, which had held sway for many years, was that excitation of the brain was always punishing and that learning and the development of behavior could be explained solely by punishment avoidance. This was called the drive reduction hypothesis. In Olds' characterization of the theory, pain supplies the push and learning based on pain reduction supplies the direction. There was no need for reward or pleasure. This model was all stick, no carrot. The pioneering experiments of Olds and Milner clearly demolished the punishment-only model in favor of a more comprehensive, hedonistic view that behavior is pulled forward by pleasure as well as pushed forward by pain. I know what you're thinking. What does it feel like for a human to have his or her medial forebrain reward circuitry stimulated with an electrode? Does it produce a crazy pleasure that's better than food or sex or sleep or even Seinfeld reruns? We do in fact know the answer to that question. The bad news is that answer comes, in part, from some deeply unethical experiments. Dr. Robert Galbraith Heath was the founder and chairman of the Department of Psychiatry and Neurology at Tulane University in New Orleans. He served from 1949 to 1980, and during that time the major focus of his work involved stimulation of the brains of institutionalized psychiatric patients, often African Americans, using surgically implanted electrodes. His main goal, to use brain stimulation to relieve the symptoms of psychiatric disorders such as major depression and schizophrenia, was laudable. However, he did not obtain proper informed consent from his patients and took decisions in experimental design that would never be approved by modern human subjects' ethical review boards. Perhaps the most egregious example was reported in a paper entitled Septal Stimulation for the Initiation of Heterosexual Behavior in a Homosexual Male, published in the Journal of Behavioral Therapy and Experimental Psychiatry in 1972.2. The rationale behind this experiment was that because stimulation of the septal area evoked pleasure, if it was combined with heterosexual imagery it could bring about heterosexual behavior in a fixed, overt homosexual male. And so patient B19, a 24-year-old male homosexual of average intelligence who suffered from depression and obsessive-compulsive tendencies, was wheeled into the operating room. Electrodes were implanted at 9 different sites in deep regions of his brain, and 3 months were allowed to pass after the surgery to allow for healing. Initially, stimulation was delivered to all 9 electrodes in turn. However, only the electrode implanted in the septum produced pleasurable sensations. When patient B19 was finally allowed free access to the stimulator, he quickly began mashing the button like an 8-year-old playing Donkey Kong. According to the paper, during these sessions, B19 stimulated himself to a point that, both behaviorally and introspectively, he was experiencing an almost overwhelming euphoria and elation and had to be disconnected despite his vigorous protests. So, not to put too fine a point on it, Heath's patient responded just as Olds and Milner's rats had. Given the chance, he would stimulate his pleasure circuit to the exclusion of all else, lest anyone think that it is only men, creatures of inherently base urges, who would respond in this manner. Another recorded case, performed by a different group, involved a woman who received an electrode implant in her thalamus, an adjacent deep brain structure, to control chronic pain. This technique has proven effective for some patients whose severe pain is not well controlled by drugs. However, in this patient the stimulation spread to nearby brain structures, producing an intense pleasurable and sexual feeling. At its most frequent, the patient self-stimulated throughout the day, neglecting her personal hygiene and family commitments. A chronic ulceration developed at the tip of the finger used to adjust the amplitude dial, and she frequently tampered with the device in an effort to increase the stimulation amplitude. At times she implored her family to limit her access to the stimulator, each time demanding its return after a short hiatus. 3 Back to patient B19. Before his brain stimulation began, he was shown a 15 minutes long stag film featuring sexual intercourse and related activities between a male and female. Not surprisingly, he was sexually indifferent to this material and even a bit angry about being made to view it. Following pleasure circuit self-stimulation, however, he readily agreed to review the film, and during its showing became sexually aroused, had an erection and masturbated to orgasm. All this in the decidedly unsexy environment of the lab. So, with the patient starting to exhibit heterosexual tendencies, what were the experimenters to do? Would he ever have an actual sexual relationship with a woman? After careful consideration of all the options and with the well-being of the patient foremost in their minds, Drs. Heath and Charles Emone made a sober medical and scientific decision, upon getting approval from the Attorney General of the state of Louisiana. They hired a hooker to come to the lab at Chelan and attempt to seduce him. She succeeded. They had sexual intercourse. The concluding sentence to the lengthy, overly descriptive paragraph describing their 2-hour-long sexual encounter reads, "Then, despite the milieu and the encumbrance of the electrode wires, he successfully ejaculated." Did patient B19 actually become heterosexual? Following discharge from the hospital, he had a sexual relationship with a married woman for several months, much to the delight of Drs. Moan and Heath, who found this development quite encouraging. His homosexual activity was reduced during this period, but did not stop completely. He still liked to turn tricks with men to earn money. Long-term follow-up information was not available. Writing in the discussion section of their scientific report, Moan and Heath were enthusiastic about the prospects for this therapy. Of central interest in the case of B19 was the effectiveness of pleasurable stimulation of new and more adaptive sexual behavior. While it's clear that patient B19 found the brain stimulation to be intensely pleasurable, I'm not convinced that he truly became heterosexual, even temporarily. It should also be cautioned that this report concerns only a single individual, not a population. This study is morally repugnant on many different levels. The profound arrogance of attempting to correct someone's sexual orientation, the medical risk of unjustified brain surgery, the gross violations of privacy and human dignity. Fortunately, homosexual conversion therapy with brain surgery and pleasure center stimulation was soon abandoned. Stepping back a bit, what we are left with, from this and a handful of other studies, is an appreciation of the immense power of direct electrical stimulation of the brain's pleasure circuitry to influence human behavior, at least in the near term. Let's now take a minute to consider some important details of the pleasure circuit. I hesitate to burden you with neuroanatomy, but just a smidgen will go a long way in explaining how we experience pleasure. We'll use the rat as an example, which is appropriate because the anatomy of the rat's pleasure circuit is very similar to that of our own. When neurons in the region called the ventral tegmental area are active, brief electrical impulses race from their cell bodies along long, thin information-sending fibers called axons. The axons have specialized structures at their endpoints called axon terminals. Some of the axon terminals of the VTA neurons are located some distance away in a region called the nucleus accumbens. When the traveling electrical spikes reach the axon terminals, they trigger the release of the neurotransmitter dopamine, which is stored in the terminals in tiny membrane-bound blobs called vesicles. When a spike enters the axon terminal, it initiates a complex series of electrical, chemical events that result in the fusion of the vesicle membrane with the membrane of the axon terminal, thereby causing the contents of the vesicle, including the dopamine neurons, to be released into a narrow fluid-filled space surrounding the axon terminal called the synaptic cleft. The dopamine molecules then diffuse and bind to specialized dopamine receptors on their target neurons, initiating a series of chemical signals therein. Neurons of the VTA also send dopamine-releasing axons to other brain regions, including the amygdala and the anterior cingulate cortex, which are emotion centers, the dorsal striatum, involved in some forms of habit learning, the hippocampus, involved in memory for facts and events, and the prefrontal cortex, a region that controls judgment and planning. In addition to sending out signals, the neurons of the VTA also receive electrochemical information from other brain regions, most notably from a group of axons, called the medial forebrain bundle, that run to it from the prefrontal cortex and other areas. The medial forebrain bundle axons release the excitatory neurotransmitter glutamate in the VTA. This causes the VTA neurons to fire spikes that propagate down their axon and then release dopamine onto their targets. The VTA dopamine neurons also receive signals from neurons in the nucleus accumbens. However, the nucleus accumbens axons release the inhibitory neurotransmitter GABA, which silences VTA neurons, preventing dopamine release for the neurons in the nucleus accumbens. In addition to receiving dopamine axons from the VTA, also receive excitatory glutamate containing fibers directly from the prefrontal cortex, the amygdala, and the hippocampus. So what does this brain circuit diagram mean for the feeling of pleasure? Here's the central insight. Experiences that cause the dopamine-containing neurons of the VTA to be active and thereby release dopamine in their targets will be felt as pleasurable, and the sensory cues and actions that preceded and overlapped with those pleasurable experiences will be remembered and associated with positive feelings. When Olds and Milner implanted electrodes to directly activate the pleasure circuit of rats, they placed them in positions that effectively stimulated the medial forebrain bundle, the axons that excite the dopamine neurons of the VTA. In fact, the electrode locations that produced the strongest pleasure were those that most effectively activated the dopamine neurons of the VTA. Likewise, Moan and Heath's patient B19 and the handful of other humans who have received pleasure from direct brain stimulation all had electrode placements that produced excitation of the VTA dopamine neurons. 5. How does activation of VTA dopamine neurons produce pleasure? Several lines of evidence indicate that catching a buzz from direct activation of the brain's pleasure circuitry with electrodes depends specifically upon release of dopamine in the target regions of the VTA neurons. Dopamine is released in these areas and diffuses across the synaptic cleft before it binds and activates receptors on the target cells to exert its effects. After it has been released, dopamine doesn't just diffuse away. Most of it is taken back up into axon terminals through the action of a protein called the dopamine transporter. The recycled dopamine is then repackaged into storage vesicles to be released again later. This means that drugs that block dopamine transporters will augment and extend the natural action of dopamine on the dopamine receptors of the target neuron, producing a more intense and longer-lasting signal. When moderate doses of drugs that block the dopamine transporter, like amphetamines and cocaine, are given to rats, they increase the amounts of lever pressing for medial forebrain bundle stimulation. This effect is most easily observed if the strength of the electrical stimulator is turned down a bit so it is not already producing maximum pleasure. Conversely, either drugs that block dopamine receptors or surgical destruction of the dopamine cells of the VTA will cause a rat that has been engaging in vigorous lever pressing for pleasurable stimulation to stop. Some psychoactive drugs work, at least in part, by hijacking the pleasure circuit. They artificially increase the effects of dopamine release from VTA neurons. Like humans, rats will self-administer certain drugs if given the chance. If you hook up a rat to a Skinner box in which lever presses deliver cocaine or amphetamines, it will press the lever repeatedly. It will do so even if it has to work very hard to achieve the desired results. That is, even if 100 lever presses are required to deliver a single tiny injection of drug. Just like Olds and Milner's rats with electrodes implanted in their pleasure circuits, and just like humans with implanted electrodes given unlimited access to brain pleasure circuit stimulation, rats allowed to self-administer cocaine and amphetamines will ignore food, water, sex, their personal hygiene, and even their young offspring in favor of the drug. With such behavior, these rat addicts are a horrifyingly accurate reflection of the ruined lives of human drug addicts. We've discussed what follows: artificial activation of the dopamine using pleasure circuit using electrodes or certain psychoactive drugs. Intense pleasure that can, in some cases, become the basis for a profound and self-destructive addiction. But what happens under the opposite circumstances? When the dopamine neurons in the pleasure circuit are damaged or destroyed, thereby reducing the amount of dopamine released and thus dialing down the rheostat of pleasure. Parkinson's disease is a neurological disorder that typically afflicts people over 50 and is more common in men than women. Its most striking symptoms involve the control of movement and include tremor, stiffness, slowness, and problems with balance and coordination. Parkinson's is chronic and progressive, usually starting with a subtle tremor but often progressing in a downward slide, resulting in difficulties with basic functions such as walking, talking, and the physical actions of eating. Some cases run in families, but most do not. While the ultimate cause of Parkinson's disease is unknown, the proximate cause is well described. It results from a loss of dopamine-containing cells in the brain, particularly in two regions, the substantia nigra and the VTA, an integral part of the pleasure circuit. At present, there is no cure for Parkinson's disease, but a number of therapies are available to treat the symptoms by increasing dopamine action to compensate for the loss of dopamine-containing neurons. One is a drug called levodopa, a chemical precursor of dopamine. When levodopa is taken up into the surviving dopamine neurons, it causes them to make more dopamine and then to boost their release of dopamine. Obviously, this depends upon there being a sufficient number of surviving dopamine neurons. If they are all dead, then levodopa therapy will fail. Another therapy is a class of drug called dopamine receptor agonists. These drugs bind to dopamine receptors and activate them, thereby mimicking the actions of dopamine. 6 levodopa and dopamine receptor agonists are often given together, and in many cases can significantly relieve the tremor and other movement problems, providing years of symptomatic relief. Unfortunately, however, as Parkinson's progresses, more and more dopamine neurons die, and as a consequence these drugs have to be given at higher and higher doses to control the symptoms. In his original 1817 description of the shaking palsy that came to bear his name, James Parkinson classified it as a pure movement disorder that left the senses and intellect uninjured. However, that assessment has turned out not to be true, and likely resulted from the surprising fact that Parkinson examined only a single shaking palsy patient in his medical office. The other 5 cases that formed the basis of his essay were merely observed and sometimes interviewed as he walked around the streets of London. 7 As early as 1913 it had become clear to some neurologists that Parkinson's disease also involved symptoms of cognition and mood and that these symptoms often preceded the onset of movement disorders. On average, Parkinson's patients tend to be introverted, rigid, stoic, slow to anger, and generally uninterested in seeking out novel experiences. They use alcohol, tobacco, and other psychoactive drugs at a much lower rate than the general population. Their personalities and actions are, in fact, the polar opposite of typical drug addicts, who are more likely to be impulsive, quick-tempered novelty seekers. Given that profile, it was quite unusual when case reports started appearing showing an unusually high incidence of pathological gambling among Parkinson's patients. In January 2001, a 64-year-old man was admitted to an outpatient treatment facility for problem gamblers in northern Italy. He had lost the equivalent of $5,000 playing slot machines over a 3-year period, causing him to become estranged from his wife and to move in with his elderly mother. He had been diagnosed with Parkinson's disease 12 years earlier and had been placed on dopamine replacement therapy, consisting of a combination of levodopa and dopamine receptor agonists. The psychiatrists at the clinic performed cognitive behavioral therapy and prescribed antidepressants. The treatment was unsuccessful, and the patient soon dropped out of the program and resumed his compulsive gambling. When he finally returned to the clinic in September 2002, the psychiatrists in charge had an insight. They asked the patient's daughter to surreptitiously monitor her father's intake of drugs. What they found was that, acting on his own, he had significantly increased his prescribed dose of both levodopa and dopamine receptor agonists. When confronted, he readily admitted increasing the dose and stated that he enjoyed the euphoric mood that accompanied it. When the drug doses were reduced to the prescribed level, his gambling stopped within a few days. In recent years, there have been a flood of similar case reports in the medical literature. 8 Analysis of these reports revealed an interesting finding. Among patients treated solely with levodopa, the incidence of compulsive gambling was very low. However, among Parkinson's patients treated with dopamine receptor agonists, there was a remarkable 8% incidence of pathological gambling. Gambling was in fact only the most common manifestation of a broad range of impulse control disorders. A small but significant population of these patients started compulsively eating, shopping, and having risky sex, all behaviors that are highly atypical for the normal Parkinson's sufferer. In almost all cases, the impulse control disorder began shortly after an increase in the dose of dopamine receptor agonist and could be terminated by reducing the dose. The best explanation for these findings is that in untreated Parkinson's disease, chronically low levels of dopamine result in a dialing down of the pleasure-reward circuit and a disinclination to seek novel experiences, and are associated with a reduced risk of addiction. In contrast, in some Parkinson's patients treated with high doses of dopamine receptor agonists, the level of dopamine action in both the pleasure circuit and associated structures is high, thereby dialing up the function of the pleasure circuit. This confers increased vulnerability to impulse control disorders and addiction. To this point, we've considered how the pleasure circuit can be artificially activated, hijacked by drugs or zapped by implanted electrodes. We've also examined the opposite case, in which the function of the pleasure circuit is attenuated in Parkinson's disease. While these stories are illuminating and help establish the existence of the pleasure circuit, we must now consider how the pleasure circuit functions naturally, in the healthy state, in the absence of artificial manipulations. Of course, the pleasure circuits of the brain have not evolved just to be activated by implanted electrodes or drugs. We must experience basic behaviors such as eating, drinking, and mating as pleasurable in order to survive and procreate. This consideration is not unique to humans. Indeed, rudimentary pleasure pathways appear quite early in evolutionary history. Even the soil-dwelling roundworm C. elegans, which is a millimeter long and has only 302 neurons in its entire body, has some basic pleasure circuitry. These worms typically feed on bacteria and are very good at following odor cues to find clumps of them. However, when a group of 8 key neurons containing dopamine are silenced, the worms are mostly indifferent to this favorite food source. To anthropomorphize, the worms just don't seem to find eating bacteria to be that much fun anymore. This indicates that some aspects of the biochemistry of pleasure appear to have been conserved through hundreds of millions of years of evolution. In both modern roundworms like C. elegans and humans, dopamine-containing neurons occupy a central position in the pleasure circuit. This evolutionary conservation, from worms to humans, speaks to the central role of pleasure in the development of behavior. In humans, rats, and other mammals, the reward circuit is much more complex, as it is interwoven with brain centers involved in decision-making, planning, emotion, and memory storage. When we find an experience pleasurable, it sets in motion several processes with different time courses. We like the experience. We associate both external sensory cues and internal cues with the experience, and these associations allow us to predict how we should behave to repeat it, and we assign a value to the pleasurable experience, so that in the future we can choose among several pleasurable experiences and determine how much effort we are willing to expend and risk we are willing to take in order to get them. Human societies strictly regulate pleasurable activities, and most have a concept of vice that's applied to unregulated indulgence in food, sex, drugs, or gambling. Using a brain scanner, it has now become possible to observe activation of the brain's pleasure circuitry in humans. Not surprisingly, this circuit is activated by vice stimuli, orgasm, sweet and fatty foods, monetary reward, and some psychoactive drugs. What's surprising is that many behaviors that we consider virtuous have similar effects. Voluntary exercise, certain forms of meditation or prayer, receiving social approval, and even donating to charity can all activate the human pleasure circuit. There's a neural unity of virtue and vice. Pleasure is our compass, no matter the path we take. As we shall discover, the evidence for a general neurobiological model of pleasure is compelling and is only growing stronger as more research is done. How, then, should we think about the pleasures, both virtues and vices, that animate our lives? That wonderful meal, the blissful feeling of connectedness during prayer, that night of great sex, the runner's high from a set morning workout, a hilarious tipsy night at the bar with friends. Are those all reducible to medial forebrain circuit activity and dopamine surges? Well, yes and no. Yes, in the sense that there seems to be a neurorheostat of reward involving the medial forebrain dopamine circuit that's engaged by almost everything we find pleasurable. No. In the sense that the activity of the pleasure circuit in isolation results in a lifeless pleasure lacking color and depth. What makes pleasure so compelling is that, through the interconnection of the pleasure circuit with other brain regions, we adorn it with memory, with associations and emotions and social meaning, with sights, sounds, and smells. A circuit-level model of pleasure shows us what is necessary but not sufficient. The transcendence and the texture emerge from the web of associated sensation and emotion that the pleasure circuit engages. Our task now shall be to explore how that all plays out in the brain.